Hello, welcome everyone to the second lecture of online video lecture series. In today's lecture, we are going to discuss Newton divided difference interpolation. I'm hopeful that you have gone through our first video lecture on Lagrange interpolation. That will help you to understand some of the ideas that we are going to discuss in this video lecture. So, today's lecture will cover the following topics: divided difference interpolation, Newton's forward difference interpolation, backward difference interpolation, and Newton's centered difference interpolation. Divided difference interpolation is similar to the Lagrange interpolation, as if we have n plus 1 data points, the order of the Lagrange polynomial will be n. And in divided difference interpolation, if we have n plus 1 data points, we are going to get a polynomial of degree n. So this means that in terms of accuracy, the Lagrange and divided difference interpolation are similar. But the method how we are going to apply them is a little different. In divided difference interpolation, we successively raise the order of the polynomial. As if you can recall, in Lagrange interpolation, all the terms in a polynomial are of order n, but that will not be the case in divided difference interpolation. Here, as you can see in equation 3.5, we have the first term of order 0, the second term of order 1, third term of order 2, and the last term of order n. So this means that we gradually raise the order of the polynomial from 0 to n. Now, as we have written the polynomial as shown in equation 3.5, we actually represent the polynomial in a different algebraic form. So divided difference interpolation is another way to represent the polynomial. Now, as we know the value of x0, we have the value of x1, and we know the value of the last node xn minus 1 and xn. So the only thing that left to calculate is the value of a0, a1, a2, and an. So we need to determine these unknown coefficients, and then we can substitute them back into 3.5 to develop the polynomial Pn of x. Now, as we know that for interpolating polynomial, it is must that it should satisfy the given data. At x is equals to x0, the function value is f of x0. So this means that our polynomial shown in 3.5 should be, when I substitute x is equals to x0, it should be equals to f of x0. By using this condition, it reduces to this form. Because when I put x is equals to x0, this term will be equals to 0. Similarly, this term will be 0. So, and the last one, this is also 0. This shows that I'm only going to get a single term, that is a0 on the right hand side. Now, solving this equation, I will get the value of a0 to be equals to f of x0. Now, second, at x is equals to x1, the polynomial value should be equals to f of x1. So use this condition in 3.5. So what I will be getting is, on the left hand side, I will have f of x1. On the right hand side, when I put x is equals to x1, this term will be a0. This will be a1 times x1 minus x0. This term will be 0 because here I have a difference with x1. x1 minus x1 is 0. And so on till the last term, it is also 0. So on right hand side, I have two terms, a0 and a1 times x1 minus x0. As we have calculated the value of a0 earlier, now I can plug that value here. So it will be f of x0 plus a1 times x1 minus x0 is equals to f of x1. Now by solving for a1, I get f of x1 minus f of x0 divided by x1 minus x0. A small activity for you. Can you calculate the value of A2? So do you have any idea how can you do that? I'm sure you are able to get my point, because you see that we have A naught to n plus 1 unknown coefficients, and we have n plus 1 nodes where we know the function value. So this means that we first put the value of function at x naught and calculated the value of A naught. Now we'll use the second at x1, plug it in 3.5 and got the value of A1. So we can do the same procedure for A2. So this means that I can repeat this procedure for A3, A4, A5, A6, and gradually I will get all the unknown coefficients from A naught to An. Now, let's start with divided difference notation. Now, we are going to link the values we have calculated in the last slide to link them with the divided difference notation. First, let's define how divided difference notation is represented. Divided difference notation, we use large brackets to represent divided difference form. So this is the zeroth order divided difference at ith node, which is actually equals to the function value at ith node. So this means that in zeroth order divided difference, the function value is equals to the zeroth order divided difference at that node. Now for the first order divided difference is being defined as at ith node, the first order divided difference is the difference of zeroth order divided difference at I plus 1 node minus zeroth order divided difference at ith node divided by the difference between the I plus 1 node and ith node. This means that it is actually the divided difference of the zeroth order divided difference. So I'm hopeful you got my point. So first order divided difference is the ratio of zeroth order divided difference to the difference between two node values. Now, second order divided difference similarly will be the divided difference of first order divided difference at ith plus 1 node minus first order divided difference at ith node divided by the difference between the node values I plus 2 and I. As you can see that as the order of divided difference is increasing, the number of node values are also increasing by 1. And if I want to connect these two, I can see that the first order divided difference at ith node was the first order divided at I plus 1 node minus first order divided difference at ith. Similarly, if we look at second order divided difference, it was first order divided difference at I plus 1th node minus first order divided difference at ith node. So following the same pattern for kth order divided difference at ith node, I can write down as for kth order divided difference at I plus 1 node minus kth order divided difference at ith node divided by the difference between I plus k and xi. Maybe this sounds you a little difficult, but it's not that. Trust me. F of x naught for nth order divided difference, we can see that nth order divided difference is actually the difference nth order divided difference at x1th node minus nth order divided difference at x naught node divided by xn minus x naught. Now, we have learned the divided difference notation. Now we are going to link this divided difference notation with the unknown coefficients that we have determined earlier. Now, the value of A naught was actually equals to function value at x naught, which is actually the zeroth divided difference at x naught. So this means that a naught is zeroth order divided difference at x naught. Now a1 value was f of x1 minus f of x naught divided by x1 minus x naught. So this means that it is actually the zeroth order divided difference at x1 minus zeroth order divided difference at x naught divided by x1 minus x naught, which is the first order divided difference. So this means that a naught is zeroth divided difference at x naught, a1 is first divided difference at x naught. So by following the same pattern, I can say that a2 is actually the second divided difference at x naught. Generally, following this pattern, I can say the ak unknown coefficient will be the kth order divided difference at x naught. A small activity for you. Can you show that the value of a2 actually equals the second divided difference? There is a hint for you to use. Use the first order divided difference at x naught node and first order divided difference at x1 node to prove the point. Now, as we have calculated the value of unknown coefficients from a naught to ak, we can generally write down the polynomial as f of x naught, which is a zeroth order divided difference, plus k is equals to 1 to n summation kth order divided difference times x minus x naught till x minus xk minus 1. So where k varies from 1 to n. So when we will expand that, we can see that actually we have used the values of a naught, a1, a2, a3 linked with the divided difference notation. So the form which we have discussed up till now seems to be a little difficult. But when we are going to develop the divided difference table, you will see that it's very, very easy. So let's discuss table 3.9, which shows the divided difference table for 6 data points, x0 to x5. Now, let's consider that we know the value of function at all these nodes, x0 to x5. As we have discussed earlier, the function value at x0 is actually the zeroth order divided difference at x0. The function value at x1 is the zeroth order divided difference at x1. The function value at x2 is the zeroth order divided difference at x2, and similarly go on. Now, the first order divided difference was the divided difference of the zeroth order divided difference. So I can write down it in the middle of these two terms. So it will be f of x1 minus f of x naught divided by x1 minus x naught. This means that I took the difference of these two values divided by the difference of these two node points and noted it in the middle. Similarly, at x1, the first order divided difference will be f of x2 minus f of x1 divided by x2 minus x1, as you can see here. We will follow the same pattern to calculate the first order divided difference at each successive point. We can see that as we calculate the first order divided difference, we have reduced the data points by 1. We started from x0 and the last first order divided difference is at x4. We have one less data point. Now, as we move to the second order divided difference, we have discussed in previous slide that it is actually the ratio of first order divided difference divided by the interval length. So the second order divided difference will be the difference of these two values divided by x2 minus x0. So interval length. Similarly, at x1 node, the second order divided difference is the difference of these two values divided by the interval length x3 minus x1. We will follow the same pattern for the successive node values. Now for the third order divided difference, we know that it is the ratio of the second order divided difference divided by interval length. So at x0 node, the third order divided difference is the difference of these two values divided by x3 minus x0. And at x1 node, it is the difference of these two values divided by x4 minus x1. And x2 node, it is the difference of these two values divided by x5 minus x2. Now, if you look at this pattern, you can see that the interval length first starts from x3 minus x0. So for third difference, it is x3 minus x0. Now, when you move to the next node, you actually move them one ahead. So x3 moves to x4 and x0 moves to x1. And you move to calculate the third order divided difference at x2. So x4 move to x5 and x1 move to x2. So this means that we can follow some kind of pattern. I'm hopeful that you are able to understand that how this divided difference table is drawn. It is very important. Keep it in mind. If you are unable to grasp the idea, please pause this video right now, do rewind it, and try to understand how table 3.9 is drawn and try to do it on paper. Once you are able to understand how this table is drawn, you will be able to grasp the upcoming ideas. But if you are stuck right now, please do pause it again. Make sure you don't move forward until you get this point, because there is no point to move forward without learning to draw this table. Now, next, I will again discuss through an example that how this table is being drawn. So let's consider an example where we need to complete a divided difference table for the given data. So we are provided with 1, 2, 3, 4, and 5 data points, and we know the function value at each of these data points. Now we are going to plot a divided difference table for this data. So first order divided difference, as you all know that the zeroth order divided difference is actually the function value at each node. And the first order divided difference is the divided difference of zeroth order divided difference divided by the interval length. Now let's discuss the table. So first of all, I have the index value I, which represents each node. So 0 corresponds to 1.0, 1 corresponds to 1.3, 2 corresponds to 1.6, and 3 index value correspond to 1.9, 4 corresponds to 2.2. So we have established a one-to-one correspondence between the node values and the index value. Now, once you have done that, we are given with the function value at each node. So we put it in the next column. So this function value is actually the zeroth order divided difference. So this means that first 3 columns of the table are drawn without making any single effort. So now let's come to the first divided difference. How we are going to draw first divided difference? I'm going to take 0.62 minus 0.765. Difference of these two terms divided by the interval length, which is shown by a red bracket, 1.0 to 1.3. So that is the value first divided difference. Now, for each successive value, you need to move 1 point ahead. I will take the difference of these two values, 0.4554 minus 0.620 divided by move 1 ahead, 1.6 minus 1.3. Now, coming to the next value, I will take 0.281 minus 0.454 divided by move ahead 1.9 to 1.6. 1.9 minus 1.6. So when after division, we will get this value. Now, for the last value, I will take the difference of these two values, 0.11036 minus 0.2818 divided by 2.2 minus 1.9. I'm hopeful that you are able to draw this fourth column of the table, and it's not difficult. Now moving to the next column, I will take the difference of these two values. Now I will increase one more data point. So it will be the divided by difference of 1.6 minus 1.0. Next, I will take the difference of these two values 0.5786120 minus times this value divided by, I will take three data points 1.9 minus 1.3, and you can see it in black. That this time we have to take the difference among three data points. For the last value, I will take the difference of these two values divided by 2.2 minus 1.6. So now you are done with the fifth column of the table. Coming to the second last column, I will take the difference of these two values and I will subtract divided by 1.9 minus 1.0 to get this value. Then I will take the difference of 0.01181 minus this term divided by 2.2 minus 1.3. And for the last one, I will take the difference of these two values 0.068 minus 0.065 divided by 2.2 to 1.0. Now you can see that as you move along the table, when you reach the last column, you are only going to get a single value. And when you get the single value, you have to divide the difference of these two values divided by 2.2 to 1.0, which means that you have included all the data points. Now, we are done with producing a divided difference table. Now, but all of these values are not useful right now. Might be, we will later discuss that how we can use the rest of the values. But the values highlighted here are of importance. Why? Because you know that the value of A naught was the zeroth order divided difference at X naught. So this means that we are only going to use those values which are the divided difference at this initial node 0. So this was the value of A naught. Now, A1 was the first order divided difference at 0th node. So this means that we are only going to use this value out of this column. So this is the value of A1. Then A2 is the second order divided difference at X naught. So we are going to use this value only. That is A2. A naught, A1, A2, A3, and A4. This means what? This means that out of this divided difference table, we are only going to use the upper diagonal values. But do remember, to generate these values, you need to completely draw this table, because to get this value, you must have this value. And to get this value, you must have these two values. And simultaneously or similarly, we can say that we need to plot this whole table. Once again, I'm saying, do make sure that you grasp the idea to generate this table and draw it on your own and then tally it with this table. Once you are able to grasp this idea, you will be able to grasp this whole lecture, because this is the fundamental concept that will be used in the coming slides. Now, once we are able to compute all these values, A0, A1, A2, A3, and A4, we are going to put these values, plug these values into the polynomial. So the polynomial will be of order 4. That is the value of A0 times A1 times X minus X naught plus A2 times X minus X naught X minus X1. Sorry, plus so on. So you can see that as we increase the number of terms, we are increasing the order of the polynomial. and the last one will be 4 differences, x minus 1, x minus 1.3, minus 1.6 and 1.9. Now do remember that the polynomial that we have shown in the first slide, 3.5, was last term is x minus xn minus 1. It was never x minus xn. So do remember, in the last term of this polynomial should restrict to x minus xn minus 1. So we have restricted here it to 1.9 rather than 2.2. So I'm hopeful you got my point. Now, let's say we want to use the polynomial to calculate the value at 1.5, which was not being provided in the table. So when you plug the value, x is equals to 1.5, you will get this answer. Now, there is a possibility that we have an equally spaced data set, like what we have seen here. In this case, all the node values are separated by a length of 0.3. So if we have equally spaced data points, then we might be able to simplify our effort. So because in that case, the difference which we have in the denominator between two nodes, we can simplify it to produce a simple formula. Now, let's consider we have equally spaced data points. This means that the x0, x1, x2, x3 up till xn, if drawn on a grid or a straight line, each one of them is being separated by a constant distance. In this case, we have assumed that to be h. So this means that x1 minus x0 will be equals to h. x2 minus x1 will be equals to h. And x3 minus x2 will be equals to h. So, or in other words, what I'm saying is, if I know the value of x0, I can approach all of these data points. How? If I have the value of x0, I should add h to get to x1. If I have value of x0, I can get to x2 by adding 2 times h. I can reach x3 by adding 1, 2, 3 times h. So this means that we should only need to have the value of x0. We can approach the rest of the nodes by adding number of times h. So this means that x0 can be written as x0 plus n times h. Now, as we know that all these nodes are equally spaced and we know the function value at each of these nodes. Now, but x is not actually the value as an integral multiple of h. X might be somewhere in the middle of x0 and x1 because it might be an unknown value. Now, if this s is an integer, this means that this x is actually one of the nodal points. But if this s is not an integer value, this means that we are going to land somewhere in the middle of two nodes. For example, if I choose s to be 1.1 by 2, so this means that I'm actually adding x0 plus half h. This means that I am approaching x0 plus half time h, that will be middle of x0 and x1. So if I have the value of s to be 3 by 2, this means that I'm going to add x0 plus 3 by 2 times h. So 3 by 2 times is 1.5 h. So that is 1 h, that is half h. So this means that I'm going to land somewhere in the middle of x1 and x2. So if we have equal spacing, h is equals to difference between the any two nodes, and x will be represented by x0 plus sh, where s can be an integer value or can be a fractional value. If s is a fractional value, we are going to land somewhere in between the nodal values. Now, I can link this thing with x minus xi. X minus xi is x naught plus sh minus x naught plus ih. By simplifying this expression, what I will get is x minus xi is s minus I times h. So this means that when I is equals to 0, x minus x naught is just equals to s times h. When I is equals to 1, it is equals to s minus 1 times h. When it's equals to 2, it is s minus 2 times h, and so on. When it is n minus 1, it is s minus n plus 1 times h. You can see that I have opened up n minus 1. So it becomes minus n plus 1. So why this is helpful? Because here in the polynomial, we have x minus x naught. So this means that for equal spacing, I don't need to do x minus x naught. Rather than I just can write s times h. Here, x minus x naught times x minus x1. So I don't need to write x minus x1. What I can do is, I can write down s minus 1 times h. This means I can reduce my labor work. So in this case, as we know that the x naught is the leftmost node value, so s should always be greater than 0 to approach the next node values. Now, by substituting this form in 3.5, we can see that we can replace a naught with the zeroth order divided difference plus a1 times x minus x naught. So x minus x naught is just s times h plus x minus x naught into x minus x1. So x minus x naught is sh, and x minus x1 is s minus 1 times h. So simplifying, we will have s minus s into s minus 1 times h square into second order divided difference, and so on. In the last term, we have the product of x minus x naught, x minus x1, x minus x2, and x minus xn minus 1. So by using the form that we have discussed in the last slide, I can write down in the form. Pause for a moment and do it again. Are you able to get that how I am replacing x minus xi's in terms of s and s minus I times h? I'm hopeful that you got it. So by looking at the pattern, I can write down it in summation form as shown here. So it's not difficult. Now we can link, as we all know that binomial coefficient form is something similar to s into s minus 1 into s minus k plus 1. So divided by k factorial. I can multiply with k factorial here and divide by k factorial to make sure that I can write down it in more compact form. So which will be sk times k factorial. So this k factorial appears here because I multiply and divide with k factorial to replace this term with the binomial coefficient form. But don't worry, we might not be regularly using this form. This form is sufficient and to use. So do remember the form is f of x naught plus sh plus s into s minus 1 plus s into s minus 1 into s minus 2 with raised in power of h until it got s minus n minus 1, which becomes s minus n plus 1 by opening the negative sign, h raised to power n. So the link you can see here is that it ends at 1, so h power is 2. It ends at n minus 1, h power is n. So I hopeful that you got the connection between these two terms. Now, as we are done with, you can see that now I just need to plug the value of S here and the value of H. I don't need to calculate all the differences x minus x naught, x minus x1, x minus x2, and so on. So now if I link it again, you can see that the value of f of x naught is this. Value of f of x naught x1 is this. Value of f of x naught x1 x2 is this, and so on. The last value is this. So we are going to use the upper diagonal values in equally spaced notation form. Now, this means that Newton divided difference formulation can be applied to equal spaced data or unequally spaced. Now, if it is unequally spaced, we will use the form of x minus xi's. And if it is equally spaced, we can replace that form with s and s minus I time h form. So do make sure that you have done this previous side as an activity and calculate these x minus xi's yourself to make sure that you grasp this idea how this polynomial is being developed. Okay, now we are going to further simplify our effort by using Newton's forward difference interpolation. In this section, we are going to replace the divided difference formulation with the ordinary differences. So here the delta sign represents the forward difference. So first order divided difference f of x naught x1 is f of x1 minus f of x naught divided by x1 minus x naught. If the data is equally spaced, this means that the difference between any two successive node values is h. So that will be equals to 1 by h time f of x1 minus f of x0. This means that I can replace the first order divided difference at 0th node with 1 by h time ordinary difference of f at x0. So the denominator x1 minus x0 is simplified with a constant value h. Now for the second order divided difference, it can be written as 1 by 2h square delta square f of x0. Second simple difference at x0 node. So following the same pattern, at f of x0 to xk divided difference can be replaced with 1 by k factorial h raised to power k delta k of f of x0. Now since f of x0 is equals to f of x0, simple function value, in Newton forward difference form, I can write down Pn of x will be equals to f of x0 plus summation k is equals to 1 to n binomial form sk delta k f of x0. Now you can see that rather than plotting or generating a table for divided difference, we need to develop a table for simple difference, which simplify our work. And moreover, h value and k factorial value are being cancelled. This means that our polynomial will be independent of h. So in terms of calculation, we have simplified it and we have reduced our labor work. Now, an activity. Now substitute the values, these values in this equation, divided difference form, and try to get this formula. Though it looks a little tricky, but once you start doing it, you will easily get to the final form. Backward divided difference interpolation. Now, if I can go to the divided difference table, you can see that the divided difference that we have used to develop the polynomial are basically all of them at the 0th node. This means that we have given the more weightage to the values that are near to the initial node 1.0. But we have not given the equal weightage to value that lies near the bottom of the table. So this means that if our data point is missing from the beginning of the table, we can use the forward difference interpolation, because in that case we are going to use these upper diagonal values. But what if the missing values lie somewhere at the bottom? In this case, it seems to me more appropriate to use these values, which are the differences in the neighborhood of the missing value, rather than using these points. So that is the logic behind the backward difference interpolation. Now, for backward divided difference interpolation, we have to define our polynomial again. And trust me, it's not difficult. We have just realigned our nodes. Rather than starting from x0 to xn, what we are going to do for backward divided difference interpolation is from xn to x0. So, as I have discussed earlier, in forward difference interpolation, we were using x0 node to approach all these data points. We can adopt the same logic for backward divided difference interpolation, that we should choose xn as our reference point, and then we can subtract h to reach xn minus 1. And similarly, by subtracting some multiple of h, I can reach x3, x2, and x1. So this means that in backward difference form, once I am given with the value of xn, I can approach all these previous node values by subtracting some multiple of h. Okay, so as you are able to grasp the idea, we will follow all the similar procedure that we have done for divided difference interpolation. That was a forward divided interpolation. We can do the same for backward divided difference interpolation. The only difference will be, now this time we are not going to use the divided difference functions at x0 node. Now, as we have chosen xn as our reference point, we will take the divided differences at xn node. So throughout your formula, we just need to replace x0 with xn. So let's start. The polynomial will be equals to the 0th order divided difference at nth node. That is actually a. Then we have first order divided difference at xn and xn minus 1. Multiply with x minus xn. So in this case, we will first approach x minus xn node, then we'll go to x minus 1 node, and then gradually we'll go to the last node, x minus x1. So you can see x minus xn, then you have a second order divided difference at nth node, x minus xn, x minus xn minus 1. And in the last term, we have the nth order divided difference at nth node. So in this case, we are going from n to 0 rather than going from 0 to n. So n to 0, x minus xn minus 1 to the last node, 1x minus x1. And do remember again, we have to skip the last node, which is x0 in this case. So here it will stop at x1. Now it will not affect the order of the polynomial, because you can see that from 1 to n, we have n multiplications of x. So this means that the order of the polynomial will still be the same, that is n. Now, once again, I'm going to express any x with xn plus sh. Now, you might have a doubt. Why not? It's xn minus sh. But it doesn't matter. For simplification and going according to the book, it doesn't matter, because in this case the value of s will be negative. So that is equivalent to xn minus sh. You can see here I have written down s is less than 0. So x taken to be xn plus sh, where s is negative. So this means that now if I have to take the difference of x minus xi's, which are in this case x minus xn, x minus xn minus 1. So x minus xi can be expressed as s plus n minus I time h. So we have adopted the similar approach by substituting these values here. So x minus xn means that I should substitute n instead of I. So that will be equals to Pn of x is equals to Pn of xn plus sh. Now do observe, here we have xn. Pn of xn plus sh. We replace the value of x with xn plus sh. Now here we have f of xn as it is, f of xn, xn minus 1 as it is, and instead of x minus xn, what I will get when I substitute n? So that will be equals to n minus n, 0. So I'm going to get sh. So you can see you have written sh here, f of xn, xn minus 1. Okay, now in next case, x minus xn will be sh, and here I'm going to get I n minus 1. So substitute n minus 1. I'm going to get s plus 1. So it is s into s plus 1 times h square times f of xn, xn minus 1, xn minus 2. So adopting the similar approach, you can calculate the last term. And believe me, you have to do it on your own to understand it 100%, because it needs some little calculations that I can't do here to make sure that we are able to reduce our video time. Otherwise, it's going to be a lengthy video. Okay, now you are done with this thing. Let's move to the Newton's backward difference interpolation. Now, the one we have discussed is divided difference interpolation, backward divided difference interpolation. Now what we are going to do is, as we have replaced the Newton's forward divided difference interpolation with just Newton's forward difference interpolation, we are going to do the same with backward divided difference interpolation. We are going to replace backward divided with backward difference interpolation. So in this case, we should have, as we have assumed earlier, that we have equally spaced data to make sure that we can simplify our procedure. So here, backward difference is being represented by a nebula Pn. A nebula Pn is the backward difference at nth node. So in this case, it is Pn minus 1. So trust me, the backward difference is just equals to forward difference at n minus 1th node. I'm hopeful you got my point. Now, when we took the higher powers, nebula k times Pn, it is just like that we have to take the backward difference of this backward difference. So we can simply write it delta k minus 1 times Pn. So we are going to take backward difference again, and again, so on. Now, the first divided difference at nth node was actually the difference of the function value at xn minus 1. So it looks to me that it will not make any difference to the divided difference table, because it was the same value. So it's equals to 1 by h times nebula f of xn. Second divided difference will be equals to 1 by 2 h square nebula square f of xn. And similarly, it's going to be 1 by k factorial hk nebula k f of xn. Now, by substituting these values in the divided difference interpolation polynomial, we're going to get f of xn plus s times nabla f of xn, s times s plus 1 divided by 2 nabla square f of xn plus so on, s plus 1 n minus 1 divided by n factorial nabla n f of x. And though it is just a little simplification process to again write down it in binomial expansion form. So you are just taking minus s as a common to make sure that we are going to use factorial. Okay, this reduced our effort, but mostly we are going to use this form. So do remember this form, and I can found a pattern here. S raised to power 1 first backward divided difference, not divided, sorry. It's only different. S raised to power 1 first divided difference. S into S plus 1 second divided difference. S plus 1 plus n minus 1, it's nth backward difference divided by n factorial. So hopefully, if you are able to grasp the Newton's forward difference interpolation, Newton's backward difference interpolation formulas. So the important thing is to remember these formulas. Now, once you are able to come to these formulas and you agree to the point that all the discussion that we have made was to prove these formulas, that how we get these formulas. Now, the important point is to apply this formula, and it's more important. So we need to understand that how we are going to apply. Now, to apply for divided difference interpolation, it's not going to make difference because in forward form, if I can quickly go back to, or should I move forward? Okay, should I move forward? Yes. So I need to move forward to make a point here. Now, for forward difference interpolation, we were using the upper diagonal values. Now, do I need to regenerate my divided difference table? No. Because backward divided difference doesn't make any difference to the formation of table. So table will still be the same. The only thing that is going to be different is that in backward difference in divided difference interpolation, now I'm going to use these values, the lower diagonal values. So this will be my first value f of xn, which is the zeroth order divided difference at nth node. First order divided difference at nth node. Second order divided difference at nth node. Third order divided difference at nth node. And definitely the last one is the fourth order divided difference at nth node. Now, we're going to discuss two examples. In one, we are going to calculate the value at 1.1, and in the other, we are going to calculate the value at 2.0. Now, to calculate the value at 1.1, as I can see that this lies in the beginning of the table. So, as per our discussion, I will prefer to use the forward difference interpolation, forward divided difference interpolation, rather than the backward divided difference interpolation, because the missing value lies in the beginning of the table. So, what I need to do, we know that our data is equally spaced. We have the divided difference values. We need to calculate the value of h. We need to have the value of s to get this polynomial. So h is equals to 2.2 minus 1.0 divided by number of intervals. So number of intervals are 1, 2, 3, and 4. So it will be equals to 1 by 3. Now, as we have discussed earlier, x is equals to x naught plus sh in forward difference interpolation. So by substituting the value of x, which is 1.1 here, x naught, which is 1.0 here, s times h here, the value of s comes to be 0.3. Now I have the value of x naught, which is 1. I have the value of h, which is 1 by 3. and I have the value of S, which is 0.3. So when I want to calculate the value at 1.1, I will substitute the value of S and H. So that is f of x naught, 0th order divided difference, first order divided difference, and second order divided difference, which are shown in red, multiply by S times H. So you can see here we have S, we have H. Then we have S times S minus 1, which is this, times H square. So S into S minus 1, S minus 2 into H cube, so on and so on. We're just substituting the values in the Newton's forward difference interpolation polynomial. And to exactly get the idea, hopefully you have written the forward difference formula on the paper, and then you can better understand this thing. Now moving to, if we want to calculate the value at 2.0, which lies at the near the end of the table. In this case, I should know that as it lies near the bottom of the table, now I will prefer to use the backward difference interpolation. Now for backward difference interpolation, once again, I need to calculate the value of H and S. So definitely H is not going to change. It's still the same 1/3. Now here, the definition of X is little different as we have done for backward difference interpolation. X is equals to Xn plus Sh. So Xn is 2.2. We want to calculate the value at 2. So X will be equals to 2. Here we can calculate the value of S, which is minus 2/3. And you can see that we have discussed it, the value of S is negative in backward difference interpolation. So we substitute here Xn, X is equals to Xn plus Sh. So Xn is 2.2, S is minus 2/3, and H is 0.3. Okay. So by substituting the values in our polynomial, now you can see that in backward difference interpolation, we are using the low diagonal values 0.1103 minus 0.57, 0.0118, 0.06, and 0.0018 with S into H. S into S plus 1 time H square, S into S plus 1, S plus 2 time H cube, and so on. So once again, to write the backward divided difference polynomial on paper and then try to understand this example. So now we are done with the forward difference interpolation and the backward difference interpolation. But we have discussed the example only for divided difference. We need to discuss the example for Newton forward difference interpolation and Newton's backward difference interpolation. So I left it as an activity for you to do. So what you are going to do is, now if you want to use the forward or backward difference formula rather than divided difference form, the difference table will be little different. And trust me, with forward and backward difference formulas, it simplifies your labor work. How? So let's discuss the table. Once again, we have considered the same example. We have 5 data points, 1, 1.3, 1.6, 1.9, and 2.2. And we have the function values at all these nodes. Now, the construction of table is a little different. Now, instead of calculating the divided difference, now we just need to calculate the ordinary differences. So in this case, it is going to be equals to 0.6200 minus 0.765. You will get this value. Then to calculate this one, 0.455 minus 0.62, you will get this value. You need to subtract these ones to get this and subtract these ones to get this. Now for second order difference, just subtract these two values. Minus 0.16 minus times this value. You get this one, minus 0.17 minus this value. And you get this value, minus 0.171 minus this value. So this means that the laborious work that we have to do for divided difference interpolation is reduced now. Now, I left the last two columns for you to complete. Complete these columns to complete a difference table for forward and backward. Now, once again, it will not make any difference. In the forward case, I'm going to use the upper diagonal values, and in the backward case, I'm going to use the lower diagonal values. So I'm hopeful that now you know that how to calculate the value of S, how to calculate the value of H. You just need to plug those values in the polynomials which we have developed for Newton's forward difference interpolation and Newton's backward difference interpolation. So just plug those values and get the answer. Now, what you can do is solve the previous example that we have done for forward and backward divided difference. Do the same examples for just Newton's forward and backward difference formula and compare the results. Now, here we have one more question. We have discussed that if the missing point lies near the beginning of the data set, we used forward interpolation. If it lies near the end of the data set, we preferred backward interpolation. Now, what if the missing point lies in the middle of the table? Now, what shall we do? Now, this makes me think I should have some other interpolation form to deal with if the missing point lies somewhere in the middle of the table. So, neither of the two that we have discussed earlier permit us to use the highest order difference close to the middle value. And as you can see in the previous slide, that for forward we use these differences, for backward we use these differences, but for central the important differences are these ones. So this means that we need to come up with and develop some new methodology to deal when the missing point lies somewhere in the middle of the table. There are several methods and they have their own advantages, but one we are going to discuss here for central difference formula is a Stirling's method. So the polynomial form that is being chosen for Stirling method will be discussed in this slide. Now, first, let's discuss how a grid is established. As we have seen that for forward, we can use x naught to approach all the nodes ahead of x naught. For backward, we can use n node to approach all the nodes behind earlier than xn. Now, in centered case, what we can do? Now, in this case, we have to choose some index values to be negative, because what we are going to do is we are going to split our table in two parts. One is the center earlier than center node, and second part below the center node values. So take the centered value to be x naught, and the values coming after x naught to be x1, x2, and x3 with positive index values, and the values earlier than x naught to be with negative index values, -1, -2, -3. Now, for Stirling's formula, once again, we are only going to discuss when we have an equally spaced data. The polynomial for Stirling's formula is given by Pn of x is equals to P2m plus 1 of x is equals to f of x naught, 0th order divided difference. And in this case, first order divided difference at -1 node plus first order divided difference at x naught node, and so on. Now, why I have replaced this n with 2m plus 1? Because in this case, this means that n is an odd number. And you know that the n is actually the index number of the last node. So this means that if we have n is an odd number, this means the total number of data points is even. Okay, how? let's look at just from x0 to x3 and take n to be 3. So in this case, we have 1, 2, 3, and 4 data points. So this means that if n is an odd number, there will be even number of data points. Now in this case, we will have a trouble to find a middle point. But if we choose n to be even 2, in this case, look, we have 1, 2. On the right, x0 is in the middle and 2 on the left. Now, so if n is odd, then we use this formula. And do remember, n does not represent the total number of nodes. It represents the index value of the last node. So this means that if you start from 0 to the last node, so n is actually representing that value. Now, if n is odd, you're going to use this formula. Now, but if n is even, n is equals to 2m. In this case, we are going to use again the same formula, but we're just going to omit this last line. There will be no last line in the formula. So rest of the formula will still be the same. So this means that the application of Stirling formula is divided into two parts. If n is even, its formula is this one. If n is, let me clarify again. If n is odd, then we are going to exactly use this formula. And if n is even, the last index value is even, in that case, we are going to omit this last one. Okay, so moving to the divided difference table. Now, as we have discussed earlier, these divided differences are about x0. So, the forward divided difference, backward divided difference, or center divided difference, the table for all of them is similar. It is the same. So, just going to do is, in this case, we are going to label, sorry. We are going to label it in a different way. It will start with negative index, come to the middle index, which is 0, and then we have a positive index values, x minus 2, x minus 1, x0, x1, and x2. And the table will be developed as similar. Now, the important divided difference that we are going to use is f of x0, x minus 1 x0, x0, x1. So you can find a pattern, first single value, then two values, then single value, then two values, and then the last value. Now, if we have an even case, so we will see how it works. Consider the table of the data points given in previous example. So we just need to apply the Stirling formula to calculate the value at 1.5. Now, in the example we have done earlier, we know that the data was starting from 1 to 2.2. So 1.5 lies somewhere in the middle of the data set. We need to calculate the value of h, which is still the same because it is just the difference between two node values, where 1 by 3, 0.3 actually. And we are going to calculate the value of x. Now, in this case, x is equals to x0 plus sh. Now, there is a difference because we have reordered indexation of our data points. So x0 lies in the middle. So x we want to calculate at 1.5, x0 is 1.6. we are given with x naught is 1.6. We calculate the value of s, which comes to be minus 1 by 3. Now, once we have the value of s, we have the values of h, have the values of d divided difference. We just need to plug those values to simplify. Now, definitely, you need to calculate the value of m here. So, substitute the n to be equals to 2m plus 1 and calculate the value of m. So, in this case, the divided difference table will be this one. So, we can see that all the values in the divided difference table are the similar as to one for forward and backward. So we indexed the middle number to be 1.6 as x naught. So that will be f of x naught, 0th order divided difference. Then we need to use two divided differences, then middle single, and then two, and then single. Okay, substitute the values in your formula. We have x naught equals to 1.6. We got the value of s, we got the value of h. And you can see that we first use this value, then we have the sum of these two values. Then we have a single value, then we have sum of these two values, and then we have a single value. By substituting it, we get the solution. Now, I do know that you have a question in your mind that what will you do? What will you do in the case if I can omit 2.2 here? If there is no 2.2 here, in this case, there is a challenge to find the middle node. Now, as per the Stirling's formula, I am going to choose 1.6 as the middle one, as the x naught, and this will be x1. This will be x minus 1 and x minus 2. Why? Because as per Stirling's formula, x naught is the node which lies close to the missing node. So if I had to calculate at 1.2, I would have chosen x naught to be 1.3. But since I need to calculate a 1.5, and by skipping the last node 2.2, so in this case, I'm going to choose x naught to be 1.6. A little tricky, but hopefully once you have done it yourself, you will get it. And do ask if you have some kind of queries. Now, we need to discuss some of the questions that we need to think after completing this lecture. What is the difference between Lagrange and divided difference interpolation? So as discussed earlier, order of the polynomial is same in the both interpolation functions, polynomials. But in divided difference interpolation, we successively raise the order of the polynomial. Now, the difference between Lagrange and divided difference interpolation is we can give the preference to divided difference interpolation because if one data point is added in Lagrange, we need to compute the whole polynomial and we need to compute all the Lagrange coefficients. But for the case of divided difference interpolation, we can simplify our effort and we just need to develop a last coefficient. And we can add in the divided difference table a last column. So in terms of accuracy, both are same. In terms of computation, to me, less effort is required for divided difference interpolation, but obviously both have their own advantages. So for integration purpose, we will prefer Lagrange rather than divided difference interpolation. So both are good. Is divided difference interpolation applicable to unequally spaced dataset? Yes. As you can see earlier, that we started with unequally spaced data points where we were taking x minus x size, difference of x minus x size. And then later stage, we convert our formulas for equally spaced data. For equally spaced data set, will we prefer difference from rather than divided difference form? Yes, for equally spaced data set, because as we have discussed earlier, that difference table construction is easier as compared to divided difference table. So it's preferable to use difference interpolation rather than divided difference interpolation. And I think there's some typing error as well. If missing data point is lying near the beginning of the data set, what interpolation is better? Definitely we'll prefer the forward difference interpolation. If it's lying near the end of the data set, we'll go for backward difference interpolation, and it's lying in the middle, we will prefer the center difference interpolation. What will be the order of polynomial if the third and onward all divided differences are 0? Now, we know that if the third divided differences are 0, this means that A3 to onward coefficients are all 0. So the order of the polynomial should be 2. Maybe you got my point. And if you skip that, try to plot a table and see if all the values in the third divided difference are 0, what will be the order of the polynomial? The last thing, assignment. So we are going to discuss few questions here. A sensor measures the position of the particle is the similar question that we have considered in the last lecture. Just the difference is this time we want to do the Newton's interpolation. Now, as you can see that the value 6 lies in the middle of the table. So I will go for center difference interpolation to perform. Even though I can do it with forward or backward, but that will not that much accurate. An engineer wants a projectile to pass through the given points. Now, once again, we need to do interpolation to find the value at 0.8. So in this case, it lies near the end of the table. So I will go for backward difference interpolation. Now, a new question: for the purpose of shrinking the trunnion into a hub, the reduction of diameter of trunnion shaft by coiling it through a temperature change is calculated by using this formula, where alpha is the thermal expansion coefficient at an average temperature. The temperature versus thermal expansion coefficient data is given in the table below. Now we have a relation between the temperature and the thermal expansion coefficient. We can see it here. Now, the problem is actually that we need to set some shaft into a hub. Now, to fix that hub, it is being cooled down to make sure that it can fit in that hole. And then it is being expanded so that it can fix there. So it is an important question where we have the relation between the temperature and the thermal expansion coefficient. So the first problem is the trunnion is cooled from 80 to 0 degree F Fahrenheit, giving the average temperature of 40 degree F. Calculate the thermal expansion coefficient at average temperature 40. Now we can see that the 40 lies near the beginning of the table. So I'm going to use the forward difference interpolation to solve this problem. In the second part, we have an average temperature of minus 129 degrees, which lies somewhere in the middle of the table. So in this case, we are going to use the central difference interpolation. And in the last case, calculate the thermal expansion coefficient at an average temperature of minus 280 degree, and minus 280 lies near the end of the table. So I'm going to use the backward difference interpolation. Now, in these cases, you can see that our data is 80 to 0, 0 to minus 60, and minus 60 to 160, 260, and 340. It's not equally spaced. So this means that we can't go for Newton forward or backward difference interpolation. We will use the divided difference interpolation to solve these parts. Now the last part, The torque speed rate of an electric motor is given in the first two rows of the table below. You need to apply the Newton's interpolation to find the value of y. It is given that the coefficient of x cube in P3 of x is 6. Now, there are two ways to do this problem. The first way is that I should develop a polynomial and then I put the value of and then calculate. The second approach can be, as I know that the coefficient of x cube is 6, this means that I know that value of A3 is 6. I can draw a divided difference table and then just calculate the value of A3, which will actually be the third divided difference in the table, and put that equals to 6 to solve this problem. That will reduce your effort. So now if you choose the first option and develop a polynomial first and then you try to solve it, you're going to take more time. So do it wisely. Using 6 data points, construct a Newton divided difference table such that the polynomial constructing using these points is a third order polynomial. Now you need to choose 6 data points. You need to construct a Newton divided difference table, but that's a little challenging problem. It should be such that the polynomial constructing using these points is a third order polynomial. So I'm not going to answer it. I'm hopeful that if you have listened to the whole lecture, you're going to solve it as well. But if you have skipped it, I will recommend go back, listen to the lecture again, and then try to solve this last assignment. With this, I'm coming to the end of the lecture. So thank you for your time. I'm hopeful that you had a good experience and you will be able to learn a lot. So take care and bye-bye.